Welcome to this fourth lecture on algorithm design. Today we're talking about search/backtracking. As we've talked about before, algorithms and data structures put together make programs, and the next major topic of computer science education is algorithms, so we're spending a little bit of time looking at some high-level ideas. And we've talked about three previous classes of algorithms. Today we'll be talking about search and backtracking. And to recap, if you can solve a problem using a greedy algorithm, that's probably your best approach. It's going to be fastest. And so on down the line, divide and conquer, dynamic programming, search, or backtracking, today's topic. These are more complex, more heavyweight approaches to solving problems. But we're trying to figure out what kinds of problems fit into these different categories. Today's topic is search problems. And these are problems that are typically stated of the form find x such that f of x is true. So find an order of a sequence of cities to visit that minimizes the cost of visiting all of those cities and returning home. That's the traveling salesman problem. And a hallmark of search problems is that oftentimes the best solution that we can come up with is just to try all possible x. And so that's why one of the reasons that this is called search is that we're going to be looking at a range of x that's basically enormous. So I just mentioned the traveling salesperson problem, or TSP. If you're given a graph and some edges connecting different, let's say, cities with their weights, try to find a tour, which is a path that connects all vertices and returns to the beginning, which is a cycle or a tour, that minimizes the total cost. So it's called the traveling salesman problem because you imagine that someone wants to sell to all these cities and get back to their home by the end of the day. So if they have to go everywhere, what's the cheapest way? And the cheapest way in this graph is highlighted in red. And you can imagine there are many tours in a large graph, many possible tours. Another example of a search problem, or a problem that we might solve with search, is a Boolean satisfiability problem. We want to find, given a sentence, what's called a sentence that looks like this, where x, y, and z are Boolean variables, we get to assign true or false to x, y, and z that makes the whole thing true, if it's possible to do so. So this says the complement of x, so if x is true, then not x, or complement of x, is false. So not x or y and z and x or not z. And it turns out that this sentence is satisfiable. It's possible to set Boolean values to x, y, and z that makes this true. And the solution, the one solution to this particular sentence, is x is true, y is true, and z is true. Another example, which you may have seen in your newspaper, is Sudoku boards. Given a board of 9 by 9 grids, cells, these are some of which are filled and some of which are empty. You get to fill in the empty ones with the numbers 1 through 9, such that every row has exactly 1 through 9, every column has exactly 1 through 9, and every square has exactly 1 through 9. And we know that, for example, we could deduce using the fact that 5 is here, there can't be any more 5s in this row. 5 is here, there can't be any more 5s in this row. And 5 is here in this column, so there can't be any more 5s in this column. So we can deduce that in this square right here, we have to place a 5 somewhere, so it must be here. Okay? Now, we call solutions of these types by different names. I've called them search, backtracking. We also call them brute force. There may be other names. I just want to talk briefly about the implications of these names. Search tells us that we're willing to look at and try any potential solution, and we're going to look at potentially a very large space of possible solutions. Backtracking, the name implies that we're going to make a sequence of decisions as our algorithm runs, and perhaps change our minds and go back to a previous decision and change that decision and then go forward. So this is kind of like depth first search, going down one path and then backing up and then going down another path. And a key part of this is that we're building, usually when using backtracking, we're building and reusing partial solutions. So we build up a part of a solution bit by bit until we get a full solution. And when we backtrack, we're only removing parts of those solutions rather than starting over from scratch, hopefully. And the name brute force you might hear thrown about just implies that we're just going to try everything. This is an expensive and thorough and perhaps aggressive technique of just trying everything. So I want to talk about two canonical types of solution strategies for search problems. When we're talking about trying everything, two very common situations you might find yourself in are that you want to solve a problem that has all combinations of things. So you're given n things, and you want to find a subset of those n things that make something true. Okay, so this is like the Boolean satisfiability problems. A subset of all the n variables you've been given should be set to true, and the remaining ones should be set to false. So if we're choosing among all possible subsets, we have 2 to the n possibilities. And that's if there are 2 options per variable. If there are more options per variable, then this would be 3 to the n or 4 to the n. Another type of problem that we run into is all permutations, which is where we're trying to come up with an ordering of n things. And those n things can be placed, we need all of those n things, and they can be placed in any order perhaps. And so the number of orderings of n things is n factorial, okay? And this is classically shown in the TSP problem where we're looking for the graph tour that we were talking about earlier. You could also think about Sudoku actually as an ordering of 9 copies of the numbers 1 through 9 in this board, although that would not be a great way to solve the problem. Regardless of which type of solution we're talking about, combinations or permutations, if you actually do try all possible options, explore the entire solution space, it's going to be very slow. And that's why we call this brute force. If you think about what a processor can do in 1 second, if you're doing 2 to the n things, then you would have to keep n under about 30 in order to process them all the options in 1 second. And if you're trying to permute n things, then you'd only be able to permute about 12 things in a second, because n factorial is just that large for n equals 12. All right, so I want to dive right in and show you sample code that should work for computing all combinations and all permutations later. So this is the all combinations. So we're trying to choose out of n things, we're trying to choose a subset of some of those n to be in our set that makes something true. Okay, so if you look down here, we have our kickoff of the recursion. So we're going to construct a set of Booleans, or really a vector of Booleans, and we're going to have n of them. And what we're going to do is pass those into this recursive function all combinations, which is defined up here. Okay, and we're going to tell it to start with option 0. That's our current. In other words, we're going to choose initially whether the 0th or the first item is in or not in the set. Okay, and our recursive code then is going to find its base case when the current reaches the end of the set. So once we've assigned each variable to be a true or false value, then we're done computing a possible solution, and then we would call some check solution method, which we're not defining here, but that would take in all the true and false values that we've computed and return true if it satisfies them, if we found a solution, in other words, or false otherwise. Okay, so this is our base case right here. And if we haven't reached our base case, then we do 2 branches of recursion. Okay, branch 1, branch 2. Branch 1 says, first let's set the variable associated with current to be false, and then let's recursively call this function on assigning the next variable next time. And if that returns true, that means we have found a solution. So we could stop here if all we're doing is looking for a solution, and we would return true because we have found a solution. Okay. Otherwise, if that didn't return true, it returned false, we're still searching for a solution. So we'll set inset of current to be true. Remember, we set it false last time. So the only difference between these 2 branches is the value of inset sub current. And then we recurse again with inset and current plus 1, the next variable, and we're just going to return that value because whatever, we were not able to find a solution with current equal to false. So if we can find a solution with current equal to true, then we'll return that value. So that's how we would compute all combinations in C++. If we want to look at computing all permutations, there are n factorial of these. We're looking at reordering a sequence of n things into all possible orderings. And again, we have our recursive code up here at the top, which we'll talk about. But let's look at the kickoff code to begin with. We have a vector of, say, integers, not booleans, and we're going to, and there are n of them, and we're going to fill the vector with values 0 through n minus 1. And then we're going to start our search by passing in the order and starting with index 0, the first one. So again, our base case is if we've reached the end of the array, then we'll check the solution, however that happens, and return that value. So we can stop at that point. Otherwise, if we're going to continue looking at constructing a solution, we're constructing these items one by one. We'll loop with I going from current up to the end of the array or the vector. And what we're going to do is we're going to do two swaps. We're going to do a swap here and a swap here. And those two swaps basically take the ith item, or sorry, the current item, which is fixed at this level of the recursion, and swaps it with the ith item, and then swaps back, and then swaps with the ith item, and swaps back. So in other words, the two swaps, swap them, and then swap them back, and then swap them, and swap them back. And I is progressing from current up to the end of the array, so we're going to swap here, here, these pairs, these pairs, these pairs, these pairs. And every time, current ends up back where it started, and so does the ith value. So those are our two swaps, and that's what's doing the reordering. And the recursion is we're going to call the recursive function on the next item. And if that's successful, we'll return true. And if we get all the way through this loop and we haven't returned true, then we can return false. Okay. Just to give you a sense for how the all permutations code would run, if n was 4, it would produce this list of total solutions, or total possible solutions. And you'll notice that the 0th item is initially 0, and we're iterating over then, or recursing on the remaining 3 items for holding this fixed, right? So how does that work? Well, initially, current is 0 and I is 0, so we're swapping I with itself, or current with itself, and then we're going to recurse on these, right? Current would be there on the first recursive call, and then current would be there, and then current would be there, and this would be our first possible solution because we're swapping current with itself, current with itself, current with itself, current with itself in these 4 recursive calls, and this would be the first potential solution. Well, after we get that one, then the next, we're going to come back up from our recursion, and current would be right here, okay? And we would swap it with the next item, I equals 3, the end. We would swap them and swap them back, okay? So if you study this, one thing you'll notice, which is kind of interesting, is that this is not in lexicographic order. In other words, it's not ordered from least to greatest if you were to order all of these arrays. And the first place that that's evident is right here, right? If you look at 0321, 0321 should not come before 0312 in lexicographic order. There are other algorithms other than the one I showed you, which can produce all permutations in lexicographic order, but that's another topic for another day. But I just wanted to point that out. Well, that's it. That's the end of the lecture. You now know how to produce all combinations of things, all permutations of things, and I'm just kidding. There's a lot more than that. We could spend an entire semester on this topic, but I do want to hit a few more details. In particular, how to make things faster. So the 2 key ideas I want to talk about for making these algorithms run faster, because as I said, If you just do the code that we've talked about so far, it's going to be slow because it's going to go through all possible combinations, permutations, or whatever. But you might be able to make it much, much, much faster if you pay attention to the structure of the problem. So the two key ideas are, let's structure our search and let's prune the search whenever possible, okay? So structuring the search, the principle here is let's use the constraints of the problem when we construct our solutions. Okay, so for example, in Sudoku, every row must have exactly one copy of each number 1 through 9. Every column must also have exactly one copy of each number 1 through 9, and each square, 3 by 3 square, must have exactly one copy of the numbers 1 through 9. So a really bad solution would be to fill in all the cells and then check if that's a solution. Okay, and when I say fill in all the cells, I mean fill it in like 1, 1, 1, 1, 1, 1, 1, 1, 1. 2, 2, 2, 2, 2, 2, 2, 2, 2, and so on down to nines all the way down here, right? That would be sort of a naive way to put all the values in all the cells. Doing this would require 9 to the 81st checks. In other words, we would have to go through 9 to the 81st boards because every cell can contain 9 values. And there are 81 cells to contend with. And that's a astronomically large number. And you'd be able to tell very early on, when I say early on, you'd be able to tell that most of these boards possibilities are infeasible early on. Like as soon as I had placed, say, a 1 next to a 1, we know that this is an infeasible board. And so the rest of filling that in is just a waste of time. Okay. So here's what I mean by structuring the search. Instead of doing that, pay attention to the structure of the problem. And first of all, let's pre-compute which cells are empty and only iterate over the empty cells. Well, obviously you would do that. It almost doesn't bear mentioning, but if you're programming this, you do want to make this a rule. But the more important idea is let's dynamically maintain lists of possible values for each row, column, and square. So if I have, this if I have some row, some column, and I have some cell right here, right? This cell is a member of this row, it's a member of this column, and it's a member of some square. The row that it belongs to might have some values filled in already, and so it might have, available only 3, 4, and 7. And this column might only have available values 3, 7, and 9. And maybe the square that it's in only has available values 7 and 9. Okay? If you intersect all three of those, the only common value between them is 7, right? 7 is common here, here, and when I said 7 and 9 was the square possible values. And so whenever we place a value in this square, say we placed a value here, let's see if I can delete this. Maybe not. If I put 7 right there in that cell, then what does that do? That deletes from this column the value 7, and it deletes from this row the value 7, and it deletes from the square the value 7 as well. So in other words, we're dynamically keeping a list for each row, for each column, and for each square, which values are available to be used for that row, column, and square. And then for each cell, we can look up which values are available among all three. Okay, and then we can only place values that are currently available and not waste our time putting in values that are clearly not going to work. So that's structuring our search. The second major idea of making search faster is pruning the search. The principle here with pruning is to identify as early as possible in the search when something is impossible or infeasible. So don't wait until you reach that base case to determine whether or not some possible solution is feasible. Check earlier than that. And in addition, you want to make that pruning check very efficient. Okay, so you want to check very early on if what you have constructed partially so far could even be made into a solution. So if you go back up here, If I were filling in a Sudoku board this way, as soon as I see that there are two ones next to each other, I can tell, well, this is an impossible solution, so we can just stop searching right here. Now, my structured search wouldn't let me do that, but the pruning should also be able to catch something like that. We want to make this pruning check efficient because we are going to be calling it a lot of times because there are a large number of possible solutions to search through. So you want to make that pruning check as efficient as possible by maintaining sort of sufficient statistics, lists, vectors, sets of things that you can look up very quickly and determine whether something is currently feasible. Another example is in the traveling salesman problem. We're trying to find an order of a bunch of vertices that leave some vertex and come back and visit every vertex and minimize the cost. Suppose that you have a known tour of cost X, whatever X is. It doesn't have to be the best tour. It doesn't even have to be a good tour, okay, in terms of the total cost. But suppose you have a tour, and that could have just been one that you just gathered by just wandering through the vertices in order or something like that. And then suppose that later in the algorithm, you are constructing a partial tour, and you realize that as you have gone from vertex to vertex to vertex, and you're adding up the cost of your path thus far, at some point that cost might get larger than X, where X is again that cost of the tour that we already knew about. If that happens, and there are no negative cost edges in this graph, then you know that no matter what you do, you can't beat that earlier tour that you already know about. So why are you continuing to search in this path? So stop what you're doing and backtrack immediately, okay? So this type of idea is what's commonly used in what are called branch and bound search solutions. We're constructing partial solutions, sort of going vertex to vertex in TSP, and we branch over possible next options that's saying from this vertex I could go here or here or here in my next step for this path. And then if I ever find that the current path cost exceeds some already known cost, then I bound any solution that gets beyond that cost, okay? And there are lots of tricks that you can use for bounding, which again, we don't have a lot of time to go into here, but these ideas of structuring your search and pruning early and pruning well and exploiting the properties of your problem can make a ridiculously slow algorithm go actually quite fast in many circumstances. It's quite fun to see how fast you can make it go. I just want to highlight that when you're pruning, if you can cut off the recursion that you're dealing with at a depth of k, so you are here and you recurse here, so here we're at depth 1, depth 0, and so on. If we can cut it off at depth k from our start of the recursion, then you save, and there are n possible steps of recursion, then you have saved 2 to the n minus k steps for that branch, or n to minus k factorial steps for that branch, depending on whether we're talking about all combinations or all permutations. So in other words, we're cutting off an entire branch. If we cut off here, we cut off an entire branch which is of size 2 to the n minus k, perhaps, or n minus k factorial. And these can be very large numbers if k is very small, if we can cut off our recursion early. So earlier pruning, lower k, is more beneficial because it cuts off a larger portion of the search space. And I just want to talk to you about this. So the order that we pick to recurse in our search does affect not the correctness of our algorithm, but it does affect the speed, okay? And this slide should have said that the order of our recursion does not affect the correctness, but can affect the speed, okay? So I want to talk, for instance, about this Boolean satisfiability problem. We get to choose true, false values for x, y, and z. And when we choose them, we can choose them in terms of x, then y, then z. So that's this search. or we can choose them in terms of ZXY or XZY or whatever. But what I want to point out is that if we choose it in order XYZ, here we've assigned no truth values. If we assigned false to X or true to X, then we reach these two states, okay? And so on. And we're only going, what we would do, of course, is we would search down here, here, to here, find out that this doesn't work, this doesn't satisfy the sentence. So we'd backtrack up to here and then go down here, find out that this doesn't work, backtrack, and we'd be here, down to here, find out it doesn't work, and so on. And the only place where we would be able to prune early is right here highlighted in red, because once we get to X is true and Y is false, we can see that this clause would be made false. X being true would make that not X be false, and Y being false would be false. So if this and this and this is false due to this assignment, so the whole thing is going to be false and we can prune early, okay? And we would prune early at this point, and then we could go down here and find that there's a solution there. If instead of going X first, then Y, then Z, right? This is all the X choices, then all the Y choices, then all the Z choices. If we went Z, then Y, I'm sorry, then X, then Y, we would be able to prune in this way. As soon as we try Z being false, we notice that that makes this clause false, and then the whole thing cannot be satisfied, so we can immediately prune this subtree. And look, we've cut off basically all this work, or the same size as all that work, which is quite a bit. So if we choose Z equals true, and then we try X is false, then Z being true and X being false would be pruned by this clause, and we can cut off these two branches, or these two subtrees, and we would continue with our search until we got down to here. So you can see that on the left, just depending on the order in which we chose our values for our variables, XYZ versus ZXY, the amount of search that we had to do was very different if we had good pruning. And so the rule of thumb that I want to impress upon you here is to recurse on the most constrained item first. And when I say the most constrained item, look at Z. It is the most constrained item. It must be true, because if it's false, then this whole thing doesn't work. So look at the variables which have the most constraints on them, choose values for them first, and then you can potentially, if those values don't work, cut off a huge amount of your search space. As opposed to on the left here, we had to look at the values of Z way down here at the bottom, and we sort of had to search the entire tree for a lot of solutions which didn't work. A few more remarks. Many problems that we're talking about today and that fit in this class are what we call NP problems. NP stands for non-deterministic polynomial, and that's short for non-deterministic polynomial time decidable. That's a theoretical concept which we don't have to go into here. But in short, a problem is an NP if we can verify its solution efficiently. In other words, if you give me a problem and you give me a solution to that problem, I can verify that that solution is a solution to the problem efficiently, if you give me both the problem and the solution, okay? That doesn't say that I can solve the problem efficiently, but it does say that I can verify a solution to the problem efficiently. It does include also all problems that we can decide efficiently in polynomial time, which we're used to, things like Dijkstra's algorithm or anything that runs in polynomial time. And a few more words about this. NP problems are very common, which is why I'm mentioning them. And a special subset are what are called NP complete. And these are what are known as the hardest NP problems. And NP complete just means that any other problem in NP, remember NP is just can be verified efficiently, solutions can be verified efficiently. Any problem in NP can be efficiently reduced or turned into an NP complete problem, okay? And this should say NP complete. Okay. So we've already discussed some topics on improving runtimes, structuring and pruning our search. Another way of improving runtimes is to not solve the problem exactly, but to solve the problem approximately. you can find, there are many cases where you can find a solution that's guaranteed to be close to optimal, but in a much faster time. So it's not the optimal answer, but you can sometimes find an answer that is guaranteed to be close to the optimal answer. And I'll just give you as an example, we've been talking about the TSP problem. There's an algorithm called Christofides algorithm for graphs which obey the triangle inequality, which is a more general way of saying the edges have weights that represent distances in the real world. Christofides algorithm runs in n squared log n time. Okay, that's much better than 2 to the n or n factorial, which is n factorial being the TSP naive solution. But it's not guaranteed to give you the optimal solution, but it is guaranteed to give you something that is within 1.5 times the optimal solution. So if the optimal solution costs 1,000, Christofides algorithm is guaranteed to give you something that's within 1,500, okay? That's all I want to say. We've barely brushed the surface. Branch and bound, search, brute force is a huge subfield of algorithms, which is very interesting, but it's not our main topic for this class. So I'm going to stop here. We've given you a taste, and next time we'll talk about randomized algorithms.